We move over to the last part of this chapter. And before we go there, remember that we could be also testing if pi 1 is greater than pi 2, if the percentage or the proportion of some population is greater than the proportion of some other population. That could be a test, and therefore the test statistic is Z, and it's kind of a tedious one. As you can see, there's a bunch of calculations there. Oh, no, that's right, I forgot. Before we go to dependence, I want to do one with the T. I should do an example with the T-distribution. So before we get to the dependent populations, let's do a independent populations with a T-distribution. Okay, so let's test. We can test. I don't know. Boston commuters spend more time commuting than do New York commuters. So, if this is the hypothesis, how are we going to designate this from a mu1, mu2 perspective? Where, let's say, mu1 is Boston and mu2 is New York. So we'll put a 1 over here for Boston and a 2 for New York. And so, if we're talking about Boston commuters on average here relative to New York commuters, what would this be? This would be what? Would this be equal to, greater than, or less than? This would be a greater than, okay? So this is what the test. Let's do it this way. So, test, is mu1 greater than mu2? All right, so what would be the alternate to this? mu1 is less than or equal to mu2. Okay, so for hypothesis testing purposes, which one of these is HO and which one is H1? This one here, mu sub 1 is less than or equal to mu sub 2 is HO, and mu sub 1 greater than mu sub 2 is the alternate. Right, now remember, Boston is 1, New York is 2. All right. What's the second step? Let's say alpha is equal to 0.01. Do we do 0.05 last time? That doesn't really matter. 0.01. What's the third step in the hypothesis test? It's take a sample. So we have n sub 1, n sub 2, we have x bar sub 1, x bar sub 2, and then we don't know sigma, and so let's say that we have to calculate S, sample standard deviation. Okay, so let's say n sub 1 is equal to, I like 100, it's always a good number, and n sub 2 is equal to 64. Did we just do that last time? 164?
No,
144, right, yeah, because although it's probably not needed, I like numbers like this because you take the square root, it's only 8, but because it's in the denominator of a fraction, I don't think it's going to matter. And so let's say that X bar in Boston is 75 minutes. And let's say in New York it's 72 minutes. And let's say we don't know sigma, we know S. Well, we don't know S, we have to calculate S. And we'll say that S is 12 minutes. And in New York, it's 20 minutes. Everybody remember, you have to know how to calculate S, sample standard deviation. Okay. What's the third step? I'm sorry, the fourth step in the hypothesis test. Test statistic. Is this a Z or a T? Well, you take out the decision tree. First question is what?
Population.
Is the population normal? We don't say anything, so you go over to the left. What's the next question?
And 30 or more.
Is N 30 or more for both of these?
Yeah. Mm-hmm.
Okay, and then what, but it's an and it says is sigma known. And the sigma's not known. Okay, so in this class, we're not gonna end up in that box. So we really have to go to the top and assume normal distributions. Okay, so I gotta write that up here now. Assume normal distributions. So we go back to the top, and are the distributions normal? Yes, you go over to the right. What's the question?
Sigma known.
Is sigma known? Answer's no. And so what do you have? You have a T. Everybody see the T?
Mm-hmm.
Okay, so this is a T. So you look at the handout, and for hypothesis testing, how many T's are there?
2.
There's 2. What separates the 2 different T's? It's
Variances.
whether or not you assume equal variances versus not assuming equal variances. Everybody see that?
Mm-hmm.
So what we're also going to do here is we're going to assume equal variances. Also have to be told that at this point in the game. Okay, so if we assume a normal distribution and assume equal variances, then we end up with the T. And so what does this T calculation look like? It's T, and this little subscript is degrees of freedom, so it's N1 plus N2 minus 2. And so it's equal to X bar 1 minus X bar 2, and then it's the square root of N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared over N1 plus N2 minus 2 times 1 over N1 plus 1 over N2. So, what we do now is we just plug in the different variables into this formula right here, or the different values into this formula. And so what do we have? It says T, well first of all, we might as well do the subscripts, meaning how many degrees of freedom are there. So, how many degrees of freedom are there? It's 164 minus 2. So there's 162 degrees of freedom. Okay, so we'll put in a little subscript here telling us how many degrees of freedom there are. And it's equal to X bar 1, which is 75, minus 72. So the numerator is going to be 3 minutes. Then we just have to do the denominator here. And so what is it? It's 100 minus 1 times 12 squared. Plus 64 minus 1 times 20 squared over 162. Because we already calculated this here as degrees of freedom at the bottom. Then it's multiplied by 1 over 100 plus 1 over 64. And so let's see what we have here. We have 3, and then I need somebody to help me out with this one.
It's, the
Nice.
bottom denominator is 2.498.
This is 2.498,
Yeah.
okay?
Someone should double check me that.
That's it. I trust you. I trust you. That's why, you know, it's sometimes it's better for me just to go to the example I have in my book. You know, everything works out nice, but what happens is I get lazy, and I'm standing over here, and I'm like, I'm not gonna go back there, just make it up. And so what happens is that we get into situations like this, but I'm thinking to myself, well, it's not really that bad, because I'll probably have somebody in here that will help me out, and you tend to help me out, but I'm also putting it up there to show the others that this is what you have to solve in order to do it. So make sure that you know how to do this arithmetic over here to be able to solve for the test statistic. And you have to do it correctly, because remember that when we do 3 divided by 2.498, what do we get? We get a, first of all, it's a plus 1.20.
1.20.
All right, and so this is a very critical number. It's called the test statistic because we're going to fit it into the decision rule in a minute. So the test statistic here is what? 1.2. Right? And so what's the 5th step in this hypothesis test? It's to formulate the decision rule. And so is this a T or a Z distribution? This is a T distribution, and I'll ask, is this a 1 or a 2-tailed test?
It's a one-tailed.
This is a 1-tailed test, and which region is the rejection region? The left, on the, correct. Over here, so this would be accept HO. This is reject HO, accept H1. And because this is a T, it really doesn't matter that the area in the table is 0.01. But what's the critical value? Well, it's a plus, first of all, and so what do? You have to go to the T table to find the critical value. And so the first thing you do look up, is this a 1 or a 2-tailed test? This is a 1-tailed test, so you're at the middle level. Alpha is 0.01, which is the 4th column in a 1-tailed test. The only thing, though, is the degrees of freedom are not on the first page, they're on the second page of the table. Because how many degrees of freedom are there?
162.
162 degrees of freedom. And so what's the table? The table only, well, after 100, it jumps up to 120. So let's see, 160, oh, look at 160, oh, they got 160 in there. That's not too bad, that's pretty close. Whereas if you go on Excel or something, they'll give you the exact T. But for our purposes, this is fine, using the number 2.35, correct?
No.
It's a 1-tailed
Oh, yeah.
test, 0.01. 2.35, everybody see that? That's right, correct? Isn't that right? 2.35? Everybody see that?
So we can round it?
160 degrees of freedom? Huh?
We can round it if it's not exactly there.
Yeah, you have to. I mean,
Yeah.
you know, what are you gonna do?
I know.
Yep. So it's 2.35. Everybody see the 2.350? 2.350, so this is a 2.350. That's the critical value. And so what's the decision rule? If the test statistic T is less than plus 2.310, then accept HO. If not, reject HO and accept H1. Okay, so that's the decision rule. And then we make the decision 6. So we take this test statistic 1.20, Where's this fit? It fits to the right of 0, but to the left of 2.312. Oh, is this a point?
2350.
2350. And so this is accept HO. And so we go back over here, we look at HO and we say, oh yeah, mu sub 1 is less than or equal to mu sub 2. And what's 1? 1 is
Boston.
sorry, we're doing Boston now. Boston, 2 is New York. So it says that Boston commuters are less than or equal to New York commuters. Now what were we trying to claim here? We were trying to claim that Boston commutes longer. And so is this a true hypothesis, or is this a true statement that Boston commuters spend more time commuting than New Yorkers?
No.
And the answer is no, at the 0.01 level of significance. So, mu1 is not greater than mu2. Okay, because everybody that's doing the test wants their question answered. And what was their question? Their question was, is this hypothesis correct? That Boston commuters spend more time? And the way we did that was to put the test itself in the alternate and make our decision based on the null hypothesis. And we would only accept this as being true if we rejected HO. And we didn't. We accepted HO. Okay? Everybody okay with T distributions and Z distributions as it relates to hypothesis testing? Two populations, two unrelated populations. Okay, ready to move on? Okay. Here's a question. Is annual NU income, NU student income, I'll do the graduate example. Is annual NU graduate, let's see, is annual income, well, I'm gonna go to, actually I'm gonna do one that I've listed here. My book, because you have to calculate the standard deviation and that takes a little bit of time, so I'll go to my notes where I already have it calculated. But before we get there, what we want to do is we want to test Northeastern pre-graduate income versus Northeastern postgraduate income. Which one is higher? You can test that in statistics. And so what would be the better way to test that hypothesis, that Northeastern income after graduation is higher than Northeastern income before graduation? There's two ways we can look at it. We can look at the current student and sample them, and we can look at the graduated student of today and sample them and look and see how those two unrelated populations fare against each other. That's one way. Or is this a better way? We take everybody here, let's say you're all ready to graduate, but you haven't graduated. We take your income right now, and then we wait, and then a year from now, we take your income again. And we compare those two populations, the population of these students before versus the population of students after. Which is the better, which do you think is the better of the two techniques?
Before and
Why would
after.
the second one be better than the first one? Why is the one where we take you before and then you after better than taking you today relative to somebody that's already graduated today?
Because they're related.
And if they are related, why is that better than if they're unrelated in this instance? My answer would be, well, it's better to take you today and you tomorrow versus you today and somebody else today, because you today versus somebody else today have other factors that are influencing income. Whereas you today, not that you're going to be the same as you tomorrow, but you're pretty much the same as you tomorrow, and you've taken out all of those differences that affect income other than you and time. And so
Degree.
and no degree, but that we're trying to measure
Yeah.
what's the influence on the student from earning a degree.
Yes.
And so the theory is that yes, taking you today is a much better, and then tomorrow is a much better way to look at how a degree affects income on NU students versus you today and others today. Do you agree with that, or not agree with that? So the object in statistics, if you're trying to test whether or not a degree means anything, is to try to rule out all these other influences upon the person, or upon the observations, or upon the populations. And so in this instance, what we have here is we have two populations. I mean, it's you before and then you after, but there's a dependency in the fact that they're testing you before and you after. And so there's a dependency of the two populations, and the dependency between the two populations is you. So, something else, another example. This is the one I think I wrote down. We have a gasoline, a current gasoline, and a new gasoline that we're trying to see if it's better. So what's a better way to test the gasoline? Take 10 cars and put the gasoline in them, have them go around a track till they run out of gas, log the miles, and then take 10 different cars and put this new gasoline in them and have them drive around and see what kind of information and data we get from that sample. So you put the old gasoline in 10 cars and you put the new gasoline in a different 10 cars. Or you put the old gasoline in 10 cars and then you put the new gasoline in the same 10 cars. Which is a better test? Definitely the second one. And so what happens is you rule out all the other influences on how a car's mileage is run, because what you've done is you've contracted it such that the two different gases are going through the same car. Well, the same cars, I should say, the same 10 cars. And so that's the dependency, that it's two populations. It's the population that runs on this gas and the population that runs on the second gas. However, the restriction is, or the dependency is we're going to use the same 10 cars. Okay, so that's the test that we're going to do right here. And so let me write down some data. And so let's see what we have here. I don't know if I did 10. Did I do 10? 1, 2, 3, 4, 5, 6, 7, 8. Yes, I did. I did 10. So we have the, okay, so we're going to test. Is mu1, well, is new gas better than existing gas, gasoline? So that's what we're going to test. And the way we're going to test it is by measuring mileage. And so if we were to test, is mu sub new relative to mu sub existing, meaning this is the average mileage from the new gas relative to the average mileage from the old gas. If we're talking about better than, what would you think this would be here? Would this be equal to, less than, or greater than?
Greater than.
This would be greater than. Everybody see that? So if this is the case, what would be the alternate? Mu sub n is less than or equal to mu sub e. Okay, so for hypothesis testing purposes, which one of these is H sub O and which one is H sub 1?
Second one.
This is mu sub n less than or equal to mu sub e. This is mu sub n greater than mu sub e. Second step, alpha 0.05. What's the third step? I'm going to move it over here. The third step is to take a sample. And we have 10 cars. And so here's the mileage that each car got. Here's X sub 1. 10, 10, 14, 11, 14, 12, 11, 11, 15, 9. Those are the 10 cars. And this is with the new gas. And then we have the existing gas. And we got 7, 12, 10, 12, 9, 10, 11, 16, 12, 13. No, we're going to need this in a minute anyway. All right, so we had 10 cars, put the new gas in, put the old gas in. Or the existing gas. And so when we have a dependency amongst the populations, what we call the test is a matched pair difference test. So this is a matched pair difference test. So it's 3 words. And the first thing we do is well, it's 3 words. The first 2 words are we match the pairs, meaning that what we're going to do is here's the first car, we put the gas in. Here's the first car, we put the existing gas in. Okay, so we're going to match the pairs. So these pairs are matched. This would be X10 over here. Okay, so we have the pairs and we matched them to the dependent car. And then it says it's a difference test, meaning that what we do now is we take the difference between the mileage here. So anytime you take a difference, it would be 10 minus the bottom of the numbers on the bottom. So what is 10 minus 7? 3. Now, one thing about the matched pair difference test is that the top numbers are the way you've designated what's on the left over here. So what's on the left? The new gas. And so when you match the pairs, because the new population is on the left, and the existing population is on the right. Over here, what happens is whatever on the left goes on top for matched paired differences. Okay, so you have to remember that whatever's on the left over here, in this case it's the new gas, is on the top. Okay, so get in the habit of doing that. And so then you take the difference. This would be a -2, this is a 4, -1, this is a 5, that's a 2, that's a 0, that's a -5, that's a 3, and that's a -4. Okay? So you take the difference, and this is the data that you use. It's the difference. That's the data that you use. These are the differences. So what you're doing is you're taking a sample of differences. And the differences will tell you whether or not there's a difference or how it differs in the new gas versus the existing gas. And so in this case over here, what's the sample size? If it's the differences, the sample size is only 10. So n is equal to 10 over here. Okay? And so what is the mean of these differences?